Today, maayong adlaw. So today we will discuss about velocity analysis. So this is topic number 5. And most of the topic that we discussed prior to this will be a great help for you to be able to master this topic as well. So the objective of this topic is for you to be able to differentiate the 4 methods of velocity analysis. Second, determine the velocity of a point in a linkage using analytical or graphical method. And finally, to use the combination of these methods to solve linear and angular velocities. So why is it necessary to solve for the velocity of the different points in a linkage? If you are familiar with different machines, as you can see, a movement of one part will compel the motion of another part. And in the design of these machine members, it is necessary to determine the velocities of these components so that we know how much or the parameter that we will use to design the different components. So you will appreciate the design of machine members when you encounter machine elements in mechanical design, which is your post-requisite for this subject. So there are 2 methods of analyzing velocities of different components of a linkage. We have the analytical method and the graphical method. So the analytical methods are more complicated. There are instances that you cannot solve the velocity using this method alone. And though the results are accurate for analytical methods, we'll have to develop certain mathematical equations and then solve the unknowns when using this method. On the other hand, the graphical method is more direct, less complicated, and still sufficiently accurate. So this method can solve the velocities and angular velocities of different components and even acceleration in a less complicated manner. This will also be the approach that we will use majority for velocity analysis and even in acceleration analysis. So there are 4 commonly used methods for velocity analysis using graphical approach. So these are the resolution and composition method, the instantaneous access of velocity method, the Centro method, the relative velocity or velocity polygon method. So prior to that, let us first go back to our knowledge on vectors. So we learned that vector quantities have both magnitude and direction. But for this case, we will deal with vectors as a process of obtaining the resultant of any number of vectors, which we call vector composition, and the reverse process wherein we're going to break up a vector into components is called vector resolution. In topic number 2, you were able to obtain the resultant of different vectors when you did your SML activities and even the graphical approach for finding the resultant, that is vector composition. So in this topic, we will use more as well about vector composition and to add to that vector resolution, wherein you are going to solve for the horizontal and the vertical components of vector. So hopefully you can still recall vector composition and vector resolution. Also, it is important for you to be able to know different scaling. This will help you make your graphical method possible. So there are 3 different scales. So the first one is the space scale, noted by the symbol Ks. So space scale can be a proportionate scale wherein you are going to reduce or to increase the dimensions of the original unit. So for example, when we say 1/4 scale, so when your machine is, for example, 100 feet, then if you will use 1/4 scale, so in your drawing, the 100 feet will be divided by 4, or will be reduced to 1/4 of the original scale. And when you decide to have a double scale, this is for very small dimensions, so you may use double scales. It can also be triple scales. So this is basically, you're going to find a proportional scale for the dimensions so that you can easily draw them in your paper. So another one is based on the number of inches on drawing equal 1 foot on the machine. For example, a 3-inch in your drawing is 1 foot in the actual machine, or 24-inch in your drawing is 1 foot in the actual machine. So this is basically equating a 1 foot on the machine to a certain inch in your drawing. Third scale is 1 inch on the drawing equals so many feet. For example, 1 inch in your drawing is 1/4 feet in the actual machine, or 1 inch in your drawing is equals to 100 feet in your actual machine. So basically, this is you trying to make your dimensions realizable and able to draw that in your paper. So the second one is velocity scale. So velocity scale is you presented by 1 inch in the drawing. But it can also be 1 centimeter in your drawing. So depending on what velocity scale or unit you are using. For this subject, I encourage you to use or represent velocity scale as 1 inch in the drawing. For example, if you have a velocity scale of 5 FPS or 5 feet per second, then every 5 feet per second in the actual machine is 1 inch, represented as 1 inch in your drawing. So that 1 inch is 5 FPS. So this will help you convert the dimensions of the velocities in your drawing to the actual velocities. So later on, you will appreciate the use of velocity scale when we solve for the actual velocities of the different components. And finally, we have the acceleration scale, or PA. So it is also represented by 1 inch in the drawing. For example, a KA of 1 feet per second squared. So it means 1 inch in your drawing is 100 feet in the actual velocities that you have computed. So those are the different scales that we will use for velocity analysis and for acceleration analysis. Another consideration is for you to be able to familiarize rotating and oscillating cranks. So it is said that the magnitude of the instantaneous linear velocity of a point on a revolving body, a rotating body, or an oscillating crank is proportional to the distance of that point from the axis of rotation of the body or a crank. So some of you are, during your topic number 3 laboratory plate, you are asking is there a velocity for an oscillating crank even if it is not rotating fully? The answer is yes. So basically the velocity, or the linear velocity, is proportional to the distance of the point on that crank from the axis of rotation. Say for example, you have this crank. So rotating at the joint with an angular velocity omega. So if you are looking for the velocities of the different points in that crank, you have to compute the radius or the distance of that point to the center of rotation. So as you can see, we have different velocities for different points, but they have the same angular velocity. So if they are of the same axis of rotation, then the angular velocity is the same. But the velocities of the different points will not be the same because, again, it is proportional to the distance of the point to the axis of rotation. And in terms of an equation, so we can write that as velocity is equals to the angular velocity times the radius. As you can see in the drawing, we have the radius of A, the radius of B, and the radius of C with respect to O. These are different. So you can expect different values of velocities for C, B, and A. And in terms of proportionality, since the angular velocity is the same, so you can rearrange the equation, and thus you can have another relationship such that the velocities, the ratios of the velocities to its radius is just constant, and that is equals to the omega. So our angular velocity is therefore just the same for the different points, even if they have different radius. So let's dig deeper to method number 1. So this is the resolution and composition method. So again, we have 4 methods of velocity analysis. So for this method of resolution and composition, if the velocity of one point and the direction of the velocity of any other point on a body are known, then the velocity of any other point on that body may be obtained by resolving the known velocity vector into components along and perpendicular to the line joining these points and making one of the components of the velocity of the other point equal to the component along that line. So I want you to take note of the following points. So if you have one point wherein the velocity and direction is known, then the velocity of any other point on that body may be obtained by resolving them into components. So when we say components, we have components long and then components perpendicular to the line. So to the line joining these points and making one of the components of the velocity of the other point, which is known, equal to the component along that line. So let us illustrate this using some example. For example, you have points A and B located on same link. So they are connected on the same link AB, as you can see in the diagram. Now the velocity of A is known, and the direction of the velocity of A is also known, and it's towards right. Now you wanted to find the velocity of B. The velocity of B is unknown, but its direction is known. The direction of B is known to be moving along this path here, as you can see. So we have velocity A, the velocity and the direction is known. And we have point B, velocity is unknown, but the direction is known along this path. And you wanted to find the magnitude of the velocity and direction of point B. So as said in the foregoing slide, you are going to resolve A into components along and perpendicular to the line joining them. So the line joining them is the line AB. Resolve A into two components along and perpendicular to the line joining AB. As you can see here, we have these components perpendicular to the line, and then we have components along the line. Now, it is also said there that you can equate that the velocities along the line equal since they are of the same line. We can say that along this line here, AB, the component of the velocity of B is equal to the component of the velocity of A. Thus, we transfer this line into point B. We call that line EA. We will transfer that to B. So this line now is equals to the line EA. So they are of equal magnitude. Then the next step is for you to draw a perpendicular line that the head of that component. So this component now is the horizontal component of the velocity of B. And this component that is perpendicular to that line is the vertical component of the velocity of B. And we all know that the velocity of B is moving in this direction, such that our velocity of B is finally, as you can see there, they're able to solve the velocity of B by resolving the known velocity into components and then equating the velocity of a particular component along the line joining them equal. And then drawing a perpendicular line to that velocity component and then connecting them along the path of another point, so that our velocity of B is moving also in this, and moving in that direction. So let us have another, so our velocity of B is BB1. What if you have 3 points? So in the same way, we're still going to resolve them into components. So say for example, you have this linkage wherein the velocity of A is known as well as its direction. So for B, so again, so you are going to resolve A into components. You have the vertical component and a horizontal component along the line joining A with B. So as you can see now, the direction is towards left because of the direction of the velocity of A. So we are going to equate that the component along the line joining them equal. So along this line AB, the component is, as you can see in the diagram. Now, we know that the direction of B, say for example, the direction of B is known and it is towards M. Then what you're going to do is to draw a perpendicular line again to the arrowhead of the component. As you can see here, we draw a perpendicular line using head to tail method. And since we know the direction of B is along M, we can find the absolute velocity of B along that line by joining again. So that's like finding the resultant, the tail of the first point to the head of the last vector. So thus we are able to obtain the absolute velocity of B as well as its direction. Now, we wanted to find as well the absolute velocity and direction at point C. So what you're going to do is first you are going to resolve again A into components along the line joining it with C. The line joining A with C is this line here. Extending that line, so we have the line AC. We are going to resolve the velocity of A along this line. We have the horizontal and the perpendicular components. So let's start first with B. So the line joining C to B is this line here as well, as you can see in the diagram. We are going to resolve B, this velocity of B, the components perpendicular and horizontal to this line joining B with C. So the perpendicular line is shown in the pink line, solid line. So, and the component along the line joining that velocity is, as you can see here, the component is your BB and the vector CC1. So component again on the line joining them should be equal of magnitude and direction. They are equal vectors, CC1 and BB. Again, we are able to obtain this vector by drawing a perpendicular line from the head of the velocity of B to the line joining them. So you now have a component for our velocity of C, CC1. On the other hand, for the line joining it with CA, so you have here, you draw again a perpendicular line, and then for the horizontal component, or the component joining them on the same line joining them, is also shown. So you have A and CC. So vector EA and vector CC are the same. These are the two vectors for our point C. We have CC1 and then we have CC. So using parallelogram method, so if you are familiar with the parallelogram method, all you have to do is to draw a line that is parallel to the two lines. So you have here, so line that is parallel to these two lines. So, and then you are going to connect that point of origination to the terminal point. So as you can see here, we are able to obtain our velocity C using parallelogram method. So this is how you can find the velocities of a point using resolution and composition methods. So basically, the requirement is just for you to know the velocity of one point as well as the direction, and then the direction of the other points, so that you can obtain the velocities that you wanted to obtain as well as its direction. So let us have an example. So we have here a mechanism. So we have a slider crank mechanism, a non-parallel slider crank, and then we have linkage QA, EB, AC, then we have DC. So the linear velocity of A is represented by the line EA. So this is the linear velocity of A. So we are looking for the linear velocity of B. What is the linear velocity of B? So we are looking for the direction and the magnitude. So there are times that you have to compute the numerical value of the velocities. So, and that's the time that you're going to use the velocity scale so that you can draw them here. So this velocities here is basically equal to 1 inch. So it's just that for this problem, we are not given with the magnitude. So all we have to do is just to find the direction as well as the velocities. So this is the given, and we wanted to find the velocity of B. So as you can see, B is restricted to move in this horizontal because this is a slider crank. And then D is restricted, constrained to move as well in this direction here. So obviously the direction of D is known, and then the direction of B is also known. It's just that we don't know its magnitude. So let us resolve again A into components. So components on the line joining A with the other points that you wanted to determine. So A is joined with B and C in this particular line here. And so we need to resolve the known velocity into components perpendicular and along this line. So this is perpendicular is your AA1, and then the horizontal is along the line is your component AA1. So by the concept that we learned, AA1 should be equal to the component of the velocity of B along this line as well as the velocity of C along this line. That's why we have this. So we are now able to obtain the components of the velocity of B along the line, that's BB1, and the components of the velocity of C along that line joining it with A, and that's CC1. So the next step is for you to determine the direction of the velocity. So again, the velocity of B is obviously also moving towards left. Because A is moving towards left, B will also move towards the left. So the direction of B is in this towards left. So we are going to create a a vector that is perpendicular to the head of B1. So this is the vector that is perpendicular to B1. And then since we know the direction of B, all we have to do is just to connect from the point of origination to the intersection to that length. So as you can see, we are able to obtain the absolute velocity of B, and that is BB. So we now have two known velocities with their directions. For C, so we are going to resolve it again using the velocities that we already know. So you are going to draw a perpendicular line. So you're going to draw a line, so connecting these three, the head. So the head of the velocities of A, absolute velocities of B. So since they are in the same line, so their head must intersect this particular line. As you can see, the head of A, the head of B, and the head of C must also intersect this line. So draw a perpendicular line to the head of C1 and intersect it with this line. So we have, then connect the origination of C to the point of intersection. That is the absolute velocity of C. So now we are able to obtain the direction of the absolute velocities of A, B, and C. So we can also find now the velocity of B. So just like what we did, we are going to resolve C into components along the line that is connecting C to D. C is connected to D in this line. So you're going to extend a line so that we can see the line that is perpendicular and the horizontal. So for the perpendicular along the line joining C and D, so we have perpendicular line CC2 from the head of C. So the component of the velocity of C along this line is equal the component of the velocity of D along that line joining them. That's why we have CC2 is equals to BD1. That is not yet, BD1 is not yet the absolute velocity of B, but it's the component of that velocity. And finally, to obtain the velocity of D, and since we know the direction of D is constrained to move in this direction, we're going to draw a perpendicular line to the head of D1. That's DD, D1D. And finally, along the direction, you draw the absolute velocity of D. That's why we have the absolute velocity of D is downwards. So as you can see, we are able to obtain the absolute velocities of A, B, C, and D using resolution and composition method. So as you can also observe, the velocity of C is larger than the rest of the velocities. So velocity of D is moving downward. Velocity of ABC is towards the left. So this is the first method of finding the velocity. There are instances when this method will not work, or when this method is enough to solve the velocity. So actually this method is very useful already because a majority of the problems of velocity analysis can be solved simply by using resolution and composition method. So let's move to method number 2. That is the instantaneous axis of velocity method. So the concept behind this method is there is one instantaneous axis for each floating link in a machine. So there is one instantaneous axis for each floating link in a machine. There is not one common instantaneous axis of velocity for all links in a machine. As you can see in topic number 4, there are different instantaneous axes for the different links in a machine. And the instantaneous axis of velocity changes position as the links moves. So in topic number 4, we call them variable or varying centros. So these are the concepts that will help us in analyzing velocity using instantaneous axis method. Say for example, you have this 4-bar linkage and you wanted to find the angular velocity of C. So for method number 1, there is no way for us to solve the angular velocity of the link number 3, the link connecting A to C, or link number 3. But using instantaneous axis of velocity method, as you can see here, the common instantaneous axis or the centro for the link. So for this link, 3 is this Q3 here. And so it is like saying that this portion here, so this imaginary line and this imaginary line, they have the same angular acceleration or angular velocity rather, since they have common centro. So the instantaneous axis of velocity method is useful in finding the angular velocity of link on a mechanism, using the idea that at a common centro, the angular velocity is the same. So as you can see, the angular velocity at A, at C, at any point here in this portion will just be constant, and that is your omega. And to solve for omega, or the angular velocity of a floating link, so this is our floating link, we can solve that simply by using the formula. Angular velocity, so of this floating link 3, is equals to the absolute velocity of A. So whenever the velocity of A is known, you just divide it by this line here from your centro to the point A. So thus we can also find the angular velocity of the floating link 3. So if you have velocity of A, and when you know this distance here from Q3A, then you can find the angular velocity of this floating link, since they are connected in the same centro. You can also solve the angular velocity of 3 or this floating link by finding the difference of the vector A1A and dividing it by the line joining them, which is AC. So this one is a vector difference. So this is not a simple vector difference. You cannot subtract it directly, but you are going to use the vector subtraction, or the negative of the vector, which was also discussed in topic number 2. So if you are going to use this formula, you have to find the components along the line, the vertical components along the line. We have A1A, and then we have C1C. So you're going to subtract the value of A1A to C1C. And the good thing is, since they are on the same link, so we are also sure that they are of the same direction, since they are perpendicular to the same link. So simply you just subtract A1A to C1C and then divide it by the length of the line joining A and C. So the good thing about this second formula is that if you cannot find this length here, because this is imaginary and usually it's not given, but this length here is given, then you can solve for the angular velocity simply by resolving the velocity of C into perpendicular components C1C and perpendicular components for A, that's A1A. So that is the second method for finding the velocity of D. So this is the same given as example number 1. It's just that we are going to use a different approach. And now we are also looking for the angular velocity of link number 4. So as you can also see, the velocity of A is known. So the first thing that you're going to do using instantaneous axis method is to determine which velocity is already known. So the velocity of A is already known, as well as its direction. So since we are looking for the velocity of D, and then D is connected to C, and C is connected to A, so the best thing that you are going to do is to find first the velocity of C, and then finally find the velocity of D using instantaneous axis. So now we're going to find a common centro or common instantaneous axis for A and C. So using topic number 4, so if you can still recall topic number 4, the instantaneous axis can be located as Q3. So all you have to do is just to extend your Q to A and then intersect that with the instantaneous axis or instant center for Q3C. So if you are able to forget this, so just go back to topic number 3. So the common center for A and C is your Q3. So again, when they are at the same instant center, so the angular velocity is just the same across in that particular region. So in this region here, so kini siya nga region, the angular velocity will just be the same. That is why the angular velocity of A is equal to the angular velocity of B, the angular velocity of C, and all other points in this particular region wherein they are rotating in the same instant center or instantaneous axis, which is Q3. So using that idea, we can find the velocity of C since we already have the velocity of A. All we have to do is just to draw an imaginary circle joining point A from the instantaneous center Q3. So we have this imaginary circle joining A from the center of a rotation, which is Q3. So the center of this circle is your point Q3. So for all points in this imaginary circle, the velocity is just equals to A. So we can say that at this point here, so since this is on the same point as the same point on the circle, but it's just equals to the velocity of A. So we can swing A to this point here. So swing A, the same magnitude on that point. So we have same magnitude of A, tangent. So tangent to this point. And then the next step is to draw a line, imaginary line, joining Q3 to the head of A and extending that line. So we have Q3A, so to the head of your velocity A. So this is your imaginary line. And to find the velocity of C, all you have to do, so since all points here are just on the same, so this must be perpendicular. So the velocity of C must also be parallel to this line here. So to the velocity of A at this line. So because if we're going to draw a circle here, so they must still be perpendicular. So that's why we are going to draw a perpendicular line at point C. So along this particular imaginary line Q3C. So that is, and the intersection of that perpendicular line to the terminal line that we draw a while ago is the velocity of C. And thus we are able to obtain the velocity of C. So now the next velocity that we will look for is the velocity of D. So since D is connected to C, we are going to use the absolute velocity of C to find the velocity of D. But before that, using again your knowledge of instantaneous center, you're going to locate the instantaneous center of this line CD. So the instantaneous center of line CD using your knowledge is at Q4. So that is actually the line that is intersecting Q3C and the intersection of Q3C and the instant center Q4D, which is at infinity. So the instantaneous center is Q4 for C and D. So we can say again that at this region here, all the angular velocity, so angular velocities are the same at this particular region. So the angular velocity of C, angular velocity of D, angular velocity of this link 4 is just the same in this region at the center of rotation QC. So they are the same angular velocity. So using that knowledge, we're going to draw again a circle. So involving C. So involving C, and then the center is at Q4. So the imaginary circle orange has a radius Q4C. And it involves C, so as you can see here. So just like what we did a while ago, all we have to do is just to swing C to the line joining Q4 to point D. So swinging it, so we have as well on the same sense. So the sense of C is clockwise. That's why the velocity at this point here, tangent to the circle, as well as to the line joining Q4D, is the same. And then draw a terminal line from Q4 to the head of C. And then since we know that the velocity D is moving in this direction, so you're going to connect point D to the point of intersection, and that is our velocity of D. So that's why we have the velocity of D is downward. So we're able to obtain the linear velocity of D. So as you can see, we have the same result as method number 1 and example number 1. Velocity of C is still the largest among all the velocities. We did not get the velocity of B since it is not required in the problem. So to find the angular velocity of link 4, we will use the formula for the angular velocity of 4, that is the velocity of C. Since all these links here are of the same angular velocity, so we can use the Centro Q4. So the velocity of C and dividing it by Q, the distance or the radius Q4C. So it's like saying that the velocity or the angular velocity of link 4 of this link 4 is just equals to the angular velocity of this particular point here. So we have the velocity of C divided by the distance from Q4 to C. Or you may also use D. So that's the velocity of D divided by the radius of Q4D. So this is a very graphical approach, but once the dimensions or the numerical value of the velocities are given, so you have to give as well the numerical value of these angular velocities by measuring this length and then using the velocity scale to convert them into the actual velocities. So basically, this is the second method of finding the velocities. So the good thing about this method, unlike method number 1, is that you can now find the angular velocity of floating links. So if you wanted to find the angular velocity of the floating link 3, so again, all you have to do is to divide the velocity of A to the line joining Q3A, or you may resolve VA into components and then use the component method to find the angular velocities. So that is the second method. So the third method is by using Centros. So some of the concept behind this is the instantaneous angular velocities of two links are inversely as the distances from their common centro to the center about which they are turning or tending to turn. So what I'm trying to see here is if you are looking for angular velocities or instantaneous angular velocities of two links. So the angular velocities of two links are Inversely, as the distances from their common centro, the centers about which they are turning or tending to turn. So basically, Centro method is almost similar to instantaneous center method or method number 2. So let us illustrate using some example. So you have here this 4-bar linkage. So using Centro method, so using the concept, so we can say that the product of the angular velocity of this link here, the floating link 3, we multiply it by the distance 2 to 1 or this distance here, or multiplying it with this distance. So the angular velocity of 3 or W3, multiplying it with this distance 2313, it is just the same as the angular velocity of 2 or this link here multiplied by the distance from its point of rotation to the common point. So that is basically what Centro method is all about. The good thing about this is if you are looking for you wanted to find the angular velocity of 3, so the floating link 3, if you know this length, and if you know the angular velocity of 2, and then if you are able to find the distance 1, 3 to 2, 3, you are able to find as well the angular velocity of this floating link 3. Because again, this is considered as a rigid region since they have common centro 1, 3. So let us illustrate that using some example. So you have here a pin jointed 4-bar mechanism as shown. So the length of AB, BC, and CD are known, as well as the length of AD. So the angle BAD is 60 degrees. At that instant, when the angle is 60 degrees, the trunk AB rotates uniformly at 100 RPM clockwise. So locate all the instantaneous centers and find the angular velocity of link BC. We're looking for the angular velocity of link BC. Given that your AB rotates clockwise, so AB rotate clockwise at 100 RPM. So from the concept, we are given with AB, we are given with omega, and we are looking for this floating link here. The only unknown that we have is the distance of this point to the centro. So wherever the centro is, we need to locate the centro and then find the distance and use the formula that we have to find the angular velocity of the floating link C. So we're given with the angular velocity, the RPM or the revolution of AB, that is 100 RPM. So you convert that RPM into angular velocity since we are looking for angular velocities. So from topic number 1 topic number 1 and 2, you were able to find angular velocities. So we have angular velocity for AB is 2 pi n. So that is converting minutes to seconds. That's why we have 10.472 rad per second. So now that we have the angular velocity AB, we need to find the centro so that we can find the distance from B to that centro. So, but before that, you have to solve first for the velocity of B. The velocity of B can be computed as the angular velocity AB, so this angular velocity times the radius, which is AB. Since AB will rotate at A, so AB is considered as the radius of rotation. That's why we have the velocity of B. So the velocity of B is the angular acceleration, WAB, times this radius AB. So let's convert it to meters so that our result is velocity of B in meter per second. So having that, we can now solve for the instantaneous center. So using topic number 4, the instantaneous centers are located as I13, I23, I24. So the useful instantaneous center here is actually I1T because this is connected to the link that is unknown, and then the rotation as well of link number 2. The velocity of B is also equals to the angular velocity BC. So this angular velocity that is unknown times the distance. So it's like what we discussed in the concept. So basically, we can rearrange this so that we can solve for the unknown, which is the angular velocity of BC. So rearranging this one, we have, and then substituting rearranging this one, but first we need to solve for the distance I3 to B. So using analytical approach, trigonometry, cosine law, and sine law, I will not deal with that because I believe that you are already good at that at this year. So the distance can be computed using trigonometry as 494.4 mm. The distance from the instantaneous center I13 to B is 494.4 mm. It's also the reason why analytical approach is kind of more complicated than the graphical approach, because when you can draw this in paper, all you have to do is just to use ruler to compute this particular length here. You can use ruler and you are using graphical approach, but when analytical approach, you just use trigonometry. So the distance is 494.4. So just substitute it here so that our angular velocity BC, the angular velocity of this floating link is 6.3 rad per second. Let us have another example. So you have a slider crank mechanism of crank OB connecting rod of length 100 meter and 400 millimeter respectively. If the crank rotates clockwise with an angular velocity of 10 rad per second, we're going to find the velocity of the slider A and the angular velocity of the connecting rod AB. So we are looking for the velocity of A. So what is the velocity of A? And the angular velocity of the connecting rod AB. So using the same approach of Centro method, we have given angular velocity of OB. This crank here is given as 10 rad per second and in clockwise direction. It is very obvious that since this is constrained to move in that direction and A is a slider crank along this horizontal, it will also move in that direction. It's just that we don't know the magnitude yet. So having that idea, so first we can solve for the known velocity. So the known velocity is simply again the angular velocity times the radius. Angular velocity is 10 rad per second, that is given, and the radius OB that we can solve for the velocity of B, that is 0.1 meter. So we have the velocity of B is 1 meter per second. Since B is connected to A, we can use Centro method. So just locate the common center for A and B. And that is at point I13. The common center is at I13 using Centro method. All you have to do is just to extend OB and then connect that to the line also that is perpendicular to the slider crank mechanism. Just draw a perpendicular line to the slider crank and then a line that is extension of this line here that from the known velocity. The technique is basically to find the Centro using shortcut method is to draw a line perpendicular to the known velocity. So the known velocity is B that is moving towards that direction. Perpendicular line is this line. Just extend that line. And then for the slider crank, that is always perpendicular to the ground. So that is for a slider crank. Whenever the ground is in the vertical direction, just use a perpendicular. So the perpendicular is this one. The intersection is the centro. So this is the centro that we will use to find the velocity of A. So using the idea, since they are now in the same center, I13, the angular velocity of A is equals to the angular velocity of B in this common center, since this is a common region for this point. This particular triangle here is a common region with the same angular velocity. So we can equate the angular velocity. It is just constant. So the angular velocity is equals to the velocity of A, which is still unknown, divided by its distance to the center, and then the velocity of B divided by its distance from the common center. So using these proportions, so we can solve for the velocity of A. All we have to do is to solve for this distance I13 to A. So again, using analytical approach, you just use a trigonometry, and using graphical approach, you can measure it with a ruler, assuming that the dimensions, the angles should be correct. So it should be 45 degrees. The length should be equals to 100 mm, 400 mm. And you may use space scale to reduce or proportional scales to reduce the drawings. Rearranging solving, so we have 464.4 mm and 556.8 mm. We can solve now for the velocity of A, just substituting the values. The velocity of A is just 0.834 meter per second. And obviously, this is also moving in the direction towards right. So how did we draw VA here? So all you have to do is use velocity scale. So if your velocity of V is 1 inch in your drawing, then since your 1 meter per second is equals to 1 inch, so depending on which velocity scale that you use, just multiply this length, or just divide this length with 1 inch so that you can get this particular distance here. That is the velocity of A. And for the angular velocity of the connecting rod AB, so all you have to do is just to go back again to our formula, since we all know that this rod A, this connecting rod, is still in the same region as rotating in the same center. So we can still use the formula that we have to solve for the angular velocity of the connecting rod AB. And since the velocities are already known, all you have to do is just to substitute this from this equation. So we have 1.79 rad per second. But using Centro method, we are still able to obtain the velocities as well as the angular velocities of a floating link. Another example for Centro method, but this one is almost similar to the instantaneous axis of rotation method. So when using Centro method, using this one, so all you have to do is using graphical approach. This is a graphical approach. First, you are going to compute the velocity of B. And then when you have the velocity of B, draw the equivalent length on B. So since this is example number 1, and we are solving it using this different method, so we're able to solve for the velocity of B. The velocity of B, again, that is just equals to your angular velocity times the radius, or this. Substitute the values here. So we have 2 pi, our n is 100, our AB is 0.3. So just solve it, then you can find the velocity of B. So how did we draw velocity of B here as such that the length is like this? So that is using your velocity scale. So we have an example later on wherein you are going to use velocity scale. For this time, we'll just use this length here that is equals to 1 inch in your drawing. The direction is moving towards right or clockwise. So locate the IC that includes the link BC. So the IC is the link that includes BC, since we are looking for the velocity BC, is this common center here. From the IC, draw a circle with radius equal to ICB. So this should include your known velocity. And then transfer the length VB to the length CD perpendicular to CD that intersect with the generated circle. So from the center to the line joining CD, you're going to move the velocity of B to that circle tangent to that particular line. Draw a line from the terminal of B in link CD to the IC. And then determine the magnitude of C by drawing a line perpendicular to CD and intersecting with the line from step number 5. So VC is perpendicular to the length joining C to the instant center. So thus we are able to find the velocity of C. So this is the velocity of C. The direction must be perpendicular to the length, to the link CD. Since all velocity should be perpendicular always to the point of rotation. As you can observe, this is perpendicular to this instant center, perpendicular to this instant center. This velocity is perpendicular to this instant center and perpendicular to this instant center. That is the Centro method for finding the velocity using graphical approach. And we have another example. This is example number 4 using Centro method again. So just resolve the known velocities and draw it in the scale that you designated using the velocity scale. Locate the IC that includes the link AB. So this is the instant center. From IC, draw a circle with radius equal to ICB. So that should include the known velocity. So this is our circle. And then transfer VB to the line ICA, just swinging it and intersect it with the generated circle. And then draw a line from the terminal of VB joining to the instant center. And determine the magnitude of A. Since A is constrained to move in the horizontal direction, all you have to do is just connect A to the terminal line that we draw from step number 5. Thus, we are able to obtain the velocity of A using graphical approach of Centro method. You have the velocity of A is moving towards right. So now we are down to our last method. For me, this is one of the easiest method to find the velocity. So using relative velocity method. Okay. The concept behind the relative velocity method. So this is done by constructing what we call velocity polygon with absolute velocities that originate from a pole Q. All lines in the velocity polygon are perpendicular to the corresponding lettered links. So some of the keywords here is your velocity polygon. So all velocities originate from the pole Q. So all lines in the velocity polygon are perpendicular. So all lines in the velocity polygon are perpendicular to the corresponding letters in the actual link. So let us demonstrate this using an example. So we have here a non-parallel equal crank mechanism, which is drawn to an original scale of 1 1/2 inch is equals to 1 feet. The crank Q2A is 9 inch long and is rotating with a uniform angular velocity of 60 RPM counterclockwise. The connecting rod AB is 3 feet 4 inches long. To determine the absolute instantaneous linear velocities of the slide B and the point P located 1 feet from A on AB and the absolute instantaneous angular velocity of AB. So we are given with the length Q to A that is 9 inch, the length of AB that is 40 inch, so 40 inch from 3 feet that is 36 inch plus 4, so that's 40 inch. And then the revolution of Q to A is counterclockwise at 60 RPM. Having this given, we are looking for the velocity of D, this slider here, the velocity of point P, the point on this link, and then the angular velocity of this floating link. So you can redraw this using actual dimensions, using actual angles that is given, using the space scale so that all the dimensions will fit in your paper. You may designate the proper space scaling. The first step is to calculate the velocity of A using the formula. So we can compute the velocity of A since the radius Q to A and the angular velocity of that link is also known. That's why we can solve for the velocity of A using a formula 2 pi Q to A n, or 2 pi Rn, right? So we have velocity of A. So we just convert it to feet per second. So since our given is in minute, we divide it by 60. Since we are in inches, we divide it by 12. Such that our result is in feet per second, or FPS. So FPS is more handy because it is lesser, and it is lesser than the other values. The velocity of A is 4.71 feet per second. So the direction of A will correspond as well to the direction of N. So the second step is to choose a velocity scale. So for this problem, I decided to choose 1 inch in my drawing is 5 FPS. So all the lines in my drawing are velocity. So this is only for velocities. So you have different scale for the link, the length of the link, the space scale. But for the velocity scale, you have different scaling, and that is 1 inch of the velocity in my drawing is 5 FPS. That is why my 4.71 FPS is basically 4.71 divided by 5 inch in my drawing. So the third step is to locate the pole Q. So pole Q may be located anywhere in your paper as long as it's comfortable with you. So I decided to put it here, the pole Q. That is the origination of all the velocities for our velocity polygon. So from Q, draw QA corresponding to the velocity of A, which is perpendicular to Q to A. So perpendicular to Q to A, so just extend Q to A so that it will reach the pole, and then draw a perpendicular line from Q. And that is 4.94 inches long. So again, 0.94 inches long is the velocities that I computed. I multiplied it with the PV. So 4.71 multiplied by 1 inch divided by 5 FPS. That's why I have 0.94 inches long. So I draw the QA. And QA now represents the velocity of A from the pole Q. So this is the velocity of A. QA is the velocity of A, that is 0.94 inches long. That is how to draw the velocity of A from the pole Q. The next step is to draw Q. Draw from Q, draw a line perpendicular to Q4B, representing VB. The next velocity that we are looking for is the velocity of B. Since A is connected to B, so it is handy to solve for B first. That is always the thing that we will do. So just solve for the points first that is at the common line from the known velocity. So velocity of A is known and B is at the same line as A. So we will solve for B first. So you are going to draw a line perpendicular to Q4B. So this is our Q4B. So this is the line Q4B. Just extend it so that it will reach your pole. And then from that line, draw perpendicular, representing the velocity of B. Because again, the velocities will always be perpendicular to that link where the rotation is happening. So the rotation of B is at Q4B. That's why we are going to draw a perpendicular line from the pole. So from Q, perpendicular to Q4B. So this is now the sense or the direction of our velocity of B. Then to solve for B, what you're going to do is to draw from A a line perpendicular to AB. So representing the direction velocity of VBA. So this line now here, so this line here is perpendicular to Q4B. And then from A, draw a line that is perpendicular to AB. This is our line AB. So this line here is perpendicular to this line AB. So let me extend the line. So this line we have AB. Since all the drawing in the velocity polygon is perpendicular to the actual, this line here is perpendicular as well. This line that we draw here, if we draw line AB, it should be perpendicular as well to AB. That's why we meant all the line in our velocity polygon is perpendicular to the actual line as well. As you can see, our QB is perpendicular to QB here. Our QA is perpendicular as well to QA, Q2A in the drawing. So that's what we meant a while ago. And thus we are able to locate, so from that perpendicular line, we can locate at the intersection. So thus, we are able to obtain QB from the point of intersection. So now we have the velocity of B because our velocity of B is represented by QB in the velocity polygon. And also we are able to find the velocity of B with respect to A, and that is AB. So the direction of the velocity of B with respect to A is from A to B. So from A to B. So the velocity of B with respect to A is from A to B. So the next step is to draw from Q a line perpendicular to Q4C. So now we are looking for the velocity of C. Since B is connected to C. So draw a line perpendicular to Q4C, representing the direction of VC. So we have this line, Q4C, and draw a line perpendicular from the pole. So from the pole, perpendicular to the extension of the line Q4C. So this is the direction of our QC. And then from B, since B is connected to C, draw a line perpendicular to BC. So you have line BC, and then draw a line perpendicular to BC from the head of B. So this now represents the velocity of C with respect to B. So at the point of intersection, you can locate the point C. which is also QC, and QC is the velocity of C. So QC is the velocity of C, and the line joining B to C, so from B to C, is the velocity of C with respect to B. The velocity of C with respect to B is BC in our velocity polygon. So thus, we are able to locate velocities of A, velocities of B, and velocity of C using this velocity polygon. So we're not yet done because we're looking for the velocities yet of D. So the next step is from Q, draw a line parallel to the path of the travel of B. So since we know that the B is constrained to move in this direction, from Q, the velocity of D will still be parallel to this line. So draw that line, is parallel to that and to that line. So we have this line here. So that is parallel to path of D. So the path of D is obviously this path here because it is constrained to move in that path. That's why we draw a parallel from Q, because all these velocities here is the actual representation of the velocities of that point as well. So that's why the velocity must be moving as well in that direction. So to solve for the velocity, draw a line from C perpendicular to CD representing BCD. So we have, so from C, so from the head of C, draw a line perpendicular to CD. So this line is perpendicular to CD. So this is perpendicular to CD, this particular line here from the head of C. And then at the point of intersection, so this is the point of intersection, that is where we can locate point P, and thus we are able to obtain the velocity QD, or velocity of D, that is QD. And then the velocity of D with respect to C is your line joining C to D. So we have velocity of A, B, C, and D, as well as the relative velocities. Velocity of B with respect to A, velocity of C with respect to B, velocity of D with respect to C. Now the first unknown is to locate, to find or to solve for the velocity of D. So the velocity of D is represented in our drawing by this length QD. All you have to do is to measure QD using ruler in the velocity polygon, and then multiply it by the velocity scale. Our velocity scale is every inch in the drawing is 5 fps. Using protractor, we are able, ruler, we are able to measure QD as 0.9 inch. Just multiply it with the velocity scale so that the actual velocity of D is 4.5 feet per second. And thus we are able to solve the first unknown. Velocity of D is 4.5 feet per second, and the direction is downward. So next, so now that we have the complete velocity polygon, so this is our complete velocity polygon. We have QA, the velocity of A, QB, the velocity of B, QC, the velocity of C, QD, the velocity of D, as well as the relative velocities. We can solve for the remaining unknowns. So the remaining unknown is the point P. So point P here, as you can see, is located here in our actual drawing, and that is along the line AB. So since all these lines here is just, these lines here are representation of this line here, so your point B must also be located between this line. So in this, along that particular line joining AB. So joining AB, and here in the velocity polygon joining AB. So by using ratio and proportion, since we know the by ratio and proportion, we can just compute for the velocity at the point where point P is located in this velocity polygon by using ratio and proportion of the length AB and the small letters AB. As you can see here, our AP divided by big letters AP is just equals to AB divided by big letter AB. And rearranging that so that we can solve for A to P. So the distance A to P is 0.249 inch. Again, AP, these are given, as well as AB is also given, that's 40. So that's why our AP is 0.249 inch by ratio and proportion. Just locate it. So it should be on the line again from A to B because this is a representation of your drawing. So AP is 0.249. The distance from A to P is 0.249 inch. Now to locate the velocity of P, all you have to do is just to connect Q to that point. So that's why we are able to obtain QP, or that is the velocity of point P. So just measure again this arrow. So we measured it as 0.94 inch and multiply it with our velocity scale, that's 5. That's why the velocity of point P is 4.7 feet per second. So we now have two unknowns. The last one is the angular velocity of AB. So for the angular velocity of AB, so we can use again our formula. So we can use the formula, the velocity of B with respect to A over AB. So for the velocity of AB, the velocity of B with respect to A divided by the length EAB. Or you may use the velocity polygon. So just measure this length here, the velocity of B with respect to A. So this is our velocity of B with respect to A. So just measure this line. So substitute it here, multiply it with the velocity scale, and then divide it by the actual length, which is AB. Or basically, this is the formula, velocity of B with respect to A divided by AB. So substituting, we have 0.82 inch. So we are able to measure this one as 0.82 inch multiplied by our velocity scale, 5 feet per second is 1 inch, divided by AB, that is given 40 inch. Just convert it to feet. That's why we have divided by 12. And then we are able to solve the angular velocity AB, that is 1.23 rad per second. Finally, we are able to solve our velocity of D, the velocity of P, and the angular velocity AB. So as you can see, your final answer should show now the direction in your actual drawing. Just copy from the velocity polygon the actual sense and the actual direction. So the velocity of D downward and then the velocity of D, P in that direction from the velocity polygon. So this is the final answer. I hope the methods are clear to you, but if you have some clarifications, you may comment below. Don't forget to subscribe. Or you may also watch this video. So these are just optional to dig deeper about resolution and composition method, instantaneous access of velocity method, the Centro method, and the velocity method for velocity polygon. So I think that's all for topic number 5. See you again.